Hi, this lesson is all about completing the Radiometric Dating Study Task. For this lesson, you're going to need the study task sheet that has all the questions on, as well as some data, and a ruler will be helpful as well. Okay, let's go. We've got two pieces of data we need to deal with. We have a block diagram with three igneous bodies labelled up A, B and C marked on it, as well as some radiometric dates. We also have a decay curve there for potassium argon dating. So, questions. We need to think about what type of igneous bodies these are. Notice there are 6 marks for this. Mark for the name, and there's a mark for a reason. We then need to work out some ages of these rocks. Okay. If you notice then the dates for location C1 and location C2, both of them in igneous body C, there's a difference between them. Discrepancy means difference, perhaps an unexpected difference. So can we explain those? Make sure though we're giving 3 good points. Also we need to think about the issues with potassium argon dating. These two answers may well be related. Again, look for the 3 points. The final question then is perhaps one that extends a little bit what you'd be asked in an exam, but I think is an important one. You could be asked about planning an investigation, a field investigation into a site like this. And this is really what we're talking about here. So if you had to go to this place for real, how would you determine the relative age? What would you actually be looking for in the rocks to work out the relative age of each of these bodies? You can't work out the radiometric age in the field, but you can work out relative ages. How would you do it? Use some sketches to illustrate your answer. Okay, now's the time. Press pause and have a go at those questions now. Okay then, let's have a look at some answers. See what you've come up with. The first question asks for the type of the igneous bodies and some reasons for that. So first of all, body A is fairly obviously a Pluton because it's large and discordant. 1 mark for Pluton, 1 mark for the reason. Body B is a dike. It's sheet-like, it's slab-like, and it's discordant, or cuts across the bedding. Discordant's the better word though. C then is a sill. It is sheet-like and concordant. Question 2. The dates shown then on figure 1 were obtained using potassium and argon dating. And this is the decay curve. So using this data, first of all we state the half-life of potassium 40. So if we read on the graph from 50% and down, we get an age of about 1200 million years. Okay. Even if your notes may say something slightly different, you always go with the data that's given. Okay, it's not a memory test, it's a skills test. You're then asked to explain what we actually mean by a half-life, and it's the time taken for half of the parent atoms to decay to daughter atoms. Mark for talking about half the time taken and the second mark is for half the parent atoms to decay. The third part of question 2 was dating igneous body A. It's got a parent-daughter ratio of 75 to 25, so to calculate the age of the rock. So again, we read across, we read down, and it's an answer of 450 million years. The other 2 marks you get are for explaining what you did to read that graph. Question 3 then asks you to describe, to explain, mustn't mix those, explain the discrepancy in the dates C1 and C2. C1 we can see as clearly within the metamorphic aureole, so it's been metamorphosed. So during metamorphism, perhaps the argon was driven out of the rock, which is going to give us an anomalously young date. You know, we've got a date there of 55 million years younger than the rest of the cell. The other thing, of course, this could actually be dating the metamorphism rather than the sill. But we have just worked out the igneous body A is 450 million years old, so this is really going to be a result of the loss of argon. Question 4 then, the potential problems. Well, we've seen argon is a gas. It gets lost from crystal lattices, particularly in orthoclase feldspar. There should be an R at the end of that, apologies. And it always then gives a younger date than we'd expect. Finally then, we have how we'd actually determine their relative age. If we're in the field, the thing we're going to be looking for is cross-cutting relationships, without much doubt. That's how we really tell these apart. But we need to develop that in a little bit more detail. So we'll be looking for things like the chilled margins. Where are these fast cooling edges? For example, we should find a chilled margin either side of the dike where it's in contact with the sill. We could also look for baked margins. Where are the baked margins? What rocks are the baked margins in? Because they must be the older ones. The rocks with the chilled margins will be the younger ones. We might even find some veining. So little veins of the younger rock being intruded into the older one. Or we could look for xenoliths, or look for intrusions that are unmetamorphosed. So the dike, for example, shouldn't show any signs of metamorphism, whereas the sill does. Any of those will get us the marks. Okay, as we watch the sunset over the Shiprock in New Mexico, which is, if you like, a volcanic neck or a mini Pluton, with some really prominent dikes or radial dikes coming off it. These radiometric dating techniques are, I think, fairly straightforward to implement. Questions on this should be, I think, very approachable if we use the data carefully. There's a little bit of learning, particularly in terms of the issues around these dating techniques. But if one of these comes up in an exam, we should be quite pleased about it. We do need to think about other radiometric dating techniques, particularly samarium neodymium, but that's for another lesson. I'll see you then.